Hello and welcome to our session. My name is Amy Johnson and I'm the Program Chair for the Associate of Arts in Early Childhood Education here at UAGC. I'm the host of this session, Beyond Screens, Teaching Coding and Computational Thinking in Early Childhood. By joining us today, you acknowledge that this session is being recorded and will be shared with TLC-related materials. Microphones will be muted for this presentation, but we encourage you to post questions and comments in the chat. Also, we have enabled live transcription. If you would like to use it, click the Show Captions button at the bottom of your Zoom window. Now, I'm pleased to introduce you to Dr. Pat Barton, Early Coordinator and Philosophy and Mathematics Instructor for the Arizona Montessori Teacher Education Program.
Thank you. Yeah, as Amy mentioned, I am I've been a Montessori teacher, or guide, for more than 20 years. And I currently work in a public Montessori program in Mesa, Arizona, and I teach children from 3 years through kindergarten. I also own and directed a Montessori program for toddlers through preschool. And then in the recent years, I have participated in the American Montessori Society's Innovation Think Tank Fellowship. And I was a part of the technology team. And at the end, hopefully I can show you some resources that were developed for all ages in some screen and some unscreened for children from actually infant, toddler, all the way through high school, looking at this lens of developing computational thinking, digital citizenship, all those pieces. So let's get started. So when you hear the term, the words coding, what comes to mind? Many people, I love this picture because it just looks like if you said to a child, think, what does it look like to think? That's what this picture looked like to me. Many people picture children instead sitting at a screen, typing lines of code, or actually right now we don't type lines of code, right? Drag and drop buttons. But in early childhood, coding isn't about technology, it's about thinking. Actually, you could argue it's about thinking all the way through. Computational thinking is a way of breaking down a problem so it can be solved logically. Today, we'll look at 4 key computational thinking processes. Researchers actually have a variety of skills they associate with computational thinking, but we'll look at 4 of the most common ones: decomposition, algorithmic thinking, debugging, and abstraction. The same thinking patterns you'll probably see in your early childhood classrooms and used in early learning. So I want you to keep that in mind as we go through the skills. We'll explore what computational thinking means and why it matters and how we can nurture these skills through playful, developmentally appropriate practices. So take a moment to think or jot down an idea or a problem solving right now with young children. Let's see. You can probably imagine a lot in the everyday routines of children that involve problem solving. So computational thinking is just a structured way to solve problems that can be broken down to be understood and even automated. The National Science Teaching Association notes that when we pair computational thinking with thoughtful scaffolds, preschoolers can practice it across many contexts, from storytelling to science. NAEYC reminds us that computational thinking aligns with how children learn through play, patterning, sequencing, and storytelling. So just as we give children rich experiences in math and language, we can also offer them experiences in computational thinking. We already do. This is a foundation for lifelong problem solving. So let's look closely at those core skills and how they might appear in your class. So once again, these are the skills we're going to talk about: pattern recognition, decomposition, abstraction, algorithmic thinking, and debugging, just through a different lens than you may already do in your classroom. So first, pattern recognition. This is easy examples are stringing beads, right? Wooden beads on a string, or block patterns. We do lots of pattern work in early childhood, noticing patterns, copying patterns, creating them, and then we don't always necessarily abstract those patterns. In the picture, you'll see there's a jar on the left that contains like white tiles. The middle jar that's open contains black tiles. So the first step in this is a little bit more complicated patterning, is that you could have children just match. We do this a lot too in the classroom, match white and black to a pattern or a grid to make designs. The next step in this is to change the zeros, and like the card on the right, and place a white tile on top of the zeros and black tiles on top of the ones. That's a next step in complexity. Then from there, you could have the children create their own patterns. So they might make a design on a grid using white and black tiles, then have them copy those white and black tiles by coloring black and white on a page, or two other colors you'd like to use. Then they could also convert that to zeros and ones. Then they could pass that to a friend, communicate that across, who then places the white and black tiles on it. And then that child could make their pattern, their illustration that the original child developed. So that's a way to make that more complex situation. The pattern recognition helps children see order and predictability, just like programmers and coders do for recurring structures in data. So when we spot patterns, we can begin to take things apart. So that is where decomposition comes in. So decomposition just means breaking down a complex problem into smaller, more manageable parts. Children do this naturally. We do it in early childhood classrooms all the time. But at home, just getting dressed, the idea of getting dressed becomes putting on shirts, pants, socks, shoes. Cleaning up becomes putting dishes away, wiping down tables, sweeping crumbs, or even smaller steps as, how about you put away the green Legos first? Or let's find all of the red crayons. We'll put them away first. That's a way to decompose a problem into small steps for a child. So if you want to take a moment to think of classroom routines that could be decomposed into smaller steps, you could add that language into your process as you're talking with children too. Once we break down things into a series of steps, we need to decide what really matters and what can benefit, what can be left out. And that's abstraction. So sometimes we've thought of abstraction as things that are concrete, like solid in front of us, and things that are more abstract, like math as a quantity of objects versus numbers that are representation of those objects. But in this situation, we're talking about abstraction as focusing on what matters, what's essential. So this reminds me of one of my favorite books by Margaret Weiss Brown, The Important Book. And I think it's a good example of abstraction. So one of the pages is the important thing about a spoon. The important thing about a spoon is that you eat with it. It's like a shovel. You hold it in your hand. You can put it in your mouth. It isn't flat. It's hollow, and it spoons things up. But the important thing about a spoon is that you eat with it. That's an abstraction, identifying the essential idea. Children do this when they're drawing a simple map to their home, or you've probably seen that's I have children in my class that are always trying to give a friend directions to get to their house, or they're making a treasure map. That's an abstraction. Only the essentials are there. Or a classroom map that only shows doors and shelves or the carpet, or when they retell a story and it just has the main events or what they consider the most important part of the story. So abstraction builds on the ability to simplify and to focus on what's mattered. So if you were to describe your classroom in three essential words, what would those be? What would be your abstraction of your classroom? When we recognize patterns or break things down and then simplify them, we can now design steps in a process. That's called algorithmic thinking. Algorithmic thinking is a series of ordered steps that accomplishes a task. Children use algorithms when they sequence picture cards for a story, or they draw steps or have steps for brushing their teeth or setting a table. Those are all repeatable steps or repeating patterns. You might have a visual schedule of your class day, right? That's helps develop algorithmic thinking. It also reassures the child of where they are in the day. Algorithmic thinking helps children express ideas clearly and then anticipate what is coming next. That's where that visual schedule is so supportive of children. And then it creates a process that others can follow. So if a child sets up a series or you set up a picture story, then someone else can tell that story based on the pictures that you presented. Or, for example, I have a substitute today and I have a visual schedule on the wall that I adjusted for today's specials we had. And the children can go in without me and know what they expect in the day, along with the substitute. I've communicated that through the algorithm. Um, Algorithmic thinking is the essence of coding, right? Providing a process that others can follow. That goes back to the black and white tiles where the child can make the zeros and ones, pass it on to a friend who then makes the design also. Montessori lessons are made of individual descriptions and precise steps. So I have a manual of a lesson for each material in the classroom. Those lessons contain steps or algorithmic thinking that build on previous experiences for the child, but also help me learn the lessons in precise detail. So I always point out to people that one of the lessons we work with is scrubbing a table. And that lesson has more than 40 steps. That's a lot of steps for a child to keep track of in doing their work. But that develops their algorithmic thinking of what comes first. So if I have water in my bucket, I have to empty it out. Or if I need water in my bucket first, I have to get the pitcher full of water. Those are lots of things to keep track of and are part of that algorithmic thinking. Even all the instructions to get onto the app, to get into Hoover, to log into this, right? All of those are providing little steps in the algorithms that you work through the day, instructions that can be repeated when you use this program or use another program that's very similar. You know where to look. It builds that thinking process. Of course, the first version of our algorithm or process isn't always correct, right? It doesn't always work perfectly or as quickly as we want, or sometimes the water gets spilled on the floor when instead of into the bucket. So the first version isn't always perfect, and that is where debugging helps. Debugging means identifying and fixing errors or mistakes or problems. In early childhood, this often looks like tinkering or trial and error. For example, building a tower that keeps falling, right? The ground is unlevel, the blocks are unsteady. That's how lots of learning happens in an early childhood classroom. It's also how adults do a lot of learning. Mixing colors is another example. Sometimes children are trying to make something purple, but it turns out to be a gray paint, or it turns to be brown paint, or it's too red and they want it to be more orange. So color mixing is another great example of a debugging process. Adults also drawing a heart. That's what I was doing the other day with a child. They really wanted to know how to draw a heart. So I broke it down into steps and I modeled how I would draw a heart and then gave them a chance. And that child's first heart somehow almost looked like an E, right? They recognized it wasn't really what they wanted it to look like. So they worked on it again in a different process and broke it down into steps. Adults can model this, really need to model this systematic approach to debugging, to test, reflect, adjust. Giving language to that is helpful. It also helps children develop resilience. We've all met children that really struggle and get easily frustrated when things don't work out the way they expected. And understanding that mistakes are a natural part of learning is essential part of the early childhood classroom. So learning to do that with adult support can develop this debugging process. So now we'll move to talking about coding, right? Which is those are all skills built into the coding, but coding is the process of creating those instructions um, with a computer that a computer understands or a person giving step-by-step instructions in order for its program or a task to work. This involves lots of spatial awareness, directional language, ordinal numbers, and task analysis. So we need to break down all of these skills in different ways. Um, So this can be done in real playful ways in the classroom. You can see it on the screen. There's a taped grid that was on the floor of my classroom, and one child is standing in the top left corner in a square. That child is the robot for the day or for that process for this code. And there's a yellow piece of paper in the spot where the children are trying to reach. There's another child that's sort of out of screen that has a series of options for instruction for the child. There's a turning arrows pointing left or right. No need to read in this situation. There's an arrow that points straight. And I think we were modeling it after one of the little robots we have. I'll show you on the next screen. And it had a noise button because that button has that little device has a button so the children could end it and have the other child go beep beep or some other noise. So the children would give each other the coder would set out the code for the other child, and then a second child would read the code forward, left, right. So we have to have that directional language. They also have to be able to place themselves in the perspective of the robot child, right? So when the robot child turns to the left, they have to turn to the left again to go the other direction. So they have to be able to take the perspective of the other child. And then this really develops a lot of collaboration. It's it's playful. It's physical. You could set this up in the classroom, but also it works really well out on a playground. And then they work together to try and solve the problem. Once it took many processes of debugging to be successful, and then we would rotate a different child would be the robot and the coder, and then the person we called the person who read the code the programmer. So this is one way to introduce coding to children. You can also do this with telling a story process through it. So there's lots of resources on how to code, giving instructions to another child, or even models moving pieces on a game board, right? So giving those kinds of instructions. So you can do this on a table too. The next sort of step in the process are these little tangible interfaces. So they don't require any screen. They're physically programmable. Robotics. And the top one is called a Bbot. The middle one is Vex123. And then the bottom one are Ozbots. I know there's a lot of other products now out there. So if you have some ideas or ones that you've used, you can put that in the chat. I like the Vex123 is the one I had in our classroom. They are not cheap, but they're the individual prices of any of those are getting to be more reasonable. And there's programs or grant programs, but also like the Science Center in Arizona is offering another one to order from. So there's lots of options to sort of move these into the classroom. The Bbot and the Vex123 work with buttons on the top. The Vex123 is designed so the kids can add different, put googly eyes on it and things like that. And what I've done is had the children just experiment with them, push forward, back, left, or there's no back. You have to go around in a circle, right? Push forward, left, or right to move through. Then you can have them set it up on a grid and follow a series of steps. Then also you can work similar to the book, to the whole body experience with the child. You can have them work together and code it, draw it out first with arrows, and then program it into the robot to get it to reach spaces. I know some teachers have also used these to do different integrate curriculum like storytelling and like finding sight words with the Bbot and things like that. The Ozbot works with different color marker. And so you have a different color it runs over the color, senses it, and tells it to do different things. So that one's a little different process, but all of those are ways to introduce this tangible interfaces that are really child friendly into classrooms. Oh, let me do a transition here first. So the last thing I want to look at is one way ideas like this can come together outside of this. So moving from the coding and looping back around to some more complex patterning and sequencing, pattern recognition, decomposition, and algorithmic reasoning and thinking. So first, I want to introduce to Pascal's triangle. So some of you might, if you're sort of a math person, you might be familiar with Pascal's triangle. We're going to do a real quick review for those of you who aren't familiar with it. This part is not something that we're going to introduce to children, but I want you to have an understanding of what's going on. And then I'll show you, if you're just give me a second, I'll show you how we can introduce this pretty complex patterning in a really fun way with children in the early childhood classroom. So Pascal triangle, we're going to build a triangle. We start with 1. We're going to add the numeral to the left and place it underneath, almost like reverse of a brick. So the second row becomes the top row is 1 plus 0, so 1 is underneath. And the top row on the right is 1 plus 0 because there's nothing there. So it has a 1 underneath. Okay, so now the second row is 1, 1. Okay, so the third row, we're adding 0 plus 1 or nothing plus 1. The first tile in the third row is 1. The next tile is 1 plus 1. Underneath it is 2. And then to the right side is 1 plus 0 is going to be 1. Now to the fourth row, the sides are always going to be 1. It's always 0 or nothing plus 1 is 1. Then if we look up to the third row, 1 plus 2 together is 3 underneath. 2 plus 1 together is 3. And then 1 on the end. And then this is the last row I've done for now, but it's 1 on the end again. 1 plus 3 is 4. 3 plus 3 in the middle, underneath it is 6. 3 plus 1 is 4 underneath it, and then the far right is 1. So there's some really cool math in here. First, the right diagonal is 1, 2, 3, 4. Then this diagonal 1, 3, 6 are triangle numbers, right? If you think of stacking blocks, if I have 1 block, right, that just makes a tower. If I have 3 blocks, I have 1, 2, right, underneath it. If I want to add another row to make to make the tower bigger, I have to add more blocks, right? So it becomes 1, 2 more in the second row, that's 3, and then the next row I have to add another step through. Dr. Johnson, I can't see the chat, so if there's something to address, just hop in, okay?
I was just saying I didn't even see the patterns coming. I was all invested in the addition, and then the patterns
Yeah,
came out. Oh, yay!
yeah, it's kind of fun. And actually, if you look at this isn't the best illustration because it's not as big, but you can see the Fibonacci numbers. If you're familiar with that, it's the pattern of 1, 1, 2, and then 3, 5, 8. So it's adding the 2 numbers before. There's a sort of wider diagonal that shows you those numbers too. So, and then if you haven't noticed this, the numbers are the 11 exponents, right? So 11 to the 0 power is 1. 11 to the first power is 11. 121 is 11 squared. 1,331 is 11 cubed. And then 14,641 is 11 to the fourth power. So lots of fun math for those math people out there. And of course, this wouldn't be the end of Pascal's triangle. You could do this forever, obviously. But that's all for this time. Now we're going to shift gears and figure out how we put this in the early childhood classroom, right? So I made this for my classroom with just tiles. I made it actually many years ago before 3D printers and things like that. So Home Depot was my friend, but I use black and white tiles. But for this, I just have them on the screen for us to use. The 2 colors I picked are my school colors that obviously the children picked a few years ago, turquoise and purple. And the pattern, the instructions or the algorithm, right, works like this. If you look at the top right, or top left, I'm sorry, I have a turquoise and a purple. Those are 2 different colors. So I'm going to put turquoise in. That's the rule. 2 different colors, I get a turquoise underneath. So whether it's turquoise purple or purple turquoise, it gets a turquoise underneath. Okay. The second rule is if they're the same color, I get a purple underneath. So whether it's turquoise turquoise or purple purple, they both get purple underneath. That's my rules. Okay. So here we go. I try and get a mat that's the same color as the one I'm not starting with. So it's a little easier for the children to understand the difference. And then in the top right, I put sort of the rule guideline. I usually have like a little picture for the children in case they need it. They do really pretty well with it, even though, because they're taking in this pattern, they're pattern seeking. So I start with a turquoise. It's turquoise purple, just like it was a 1 before, and turquoise purple. So my next row is going to be turquoise turquoise. Okay. So now I have the third row. I have it turquoise because it's two different colors. The two turquoise on row 2, I have to put a purple underneath because they're the same. And then the right is going to be turquoise. So just like in the number version, my sides are always turquoise, are always one. This one, the sides are always going to be turquoise because it's always going to be two different colors. Okay, so now, oh, this is where it kind of throws a different way of looking at patterning, right? Because I would expect there should be some more purple. And why do I have a whole row of purple? But it's purple turquoise gets a turquoise. Turquoise purple gets a turquoise. Purple turquoise gets a turquoise. Turquoise purple gets a turquoise. So now I have a whole row. Now take a minute and predict what do you think is going to be next, or what patterns emerging? And I would ask the child to do this with me too. So we work through this together. Now I'm in a Montessori classroom, so I would do this with like 1 or 2 children, but you could do this in a small group. You could do it on a wall kind of thing. Okay, third row, or 1, 2, 3, 4, 5, fifth row. Purple turquoise. It's going to be turquoise again. The two turquoise purple, two turquoise in the middle. I got to put a purple there. They're the same. Two turquoise on the side. Got to put a purple there. Then the end, turquoise purple gets a turquoise. Okay, so now I just inlaid so you can see the numbers on top of the colors we just set up. And what do you notice? Odd numbers are turquoise and even numbers are purple. Now, if you expand this out, which I would do with the child with just the tiles, you get this. And that gives you a whole nother set of patterns. You can actually make this with triangles, and then you get the inverse of a triangle. Or if you do a lesson, I have one in my classroom that has 4 equilateral triangles, right? You can see that equilateral, you can see those 4 bigger equilateral triangles with the middle equilateral is purple. So you can expand on that in lots of different ways. So something as old as Pascal's triangle, or as complex in thinking and patterning, becomes a playful way to nurture computational thinking, lots of different ways of sequencing, following rules, repeating a pattern, and engaging the child in this other way of seeing something that might that is fun and interesting and playful and has this deeper math concept to that. So back to our role as an adult. So of course, always setting up the environment so they have the opportunity to do access things that help them develop these skills. Asking guiding questions without solving it for them. That's really hard. It's always hard in early childhood, I know. But it's especially hard, but we have to give them that chance to struggle with it, scaffolding gently. And it can be especially challenging and frustrating. But we have to, they benefit in the end by going through that process, and helping them develop it. Sometimes they also come up with solutions, of course, often that you didn't think of. And then modeling mistake making all the time, right? You want to do that in the classroom. That's sort of a general expectation of a teacher, right? Sometimes it's on purpose. Sometimes I make mistakes that aren't on purpose, and how I react to that models for the children, and then encouraging that persistence. So let's see. Now, why it matters, just a little bit about what we talked about. So coding is now sometimes referred to as the new literacy. It begins with not with screens, but with thinking. And actually, we were talking a little bit about AI. I've had lots of conversations outside of here about AI, and some question about whether AI replaces coding and things like that. But at this level, we're really developing their problem-solving skills, their logical thinking, their ability to break down things into small steps, abstract important information, and think creatively. So when we integrate computational thinking into storytelling, into play, into everyday routines, we prepare the children for a world that involves curiosity. It also adds a lot of collaboration. It has open-ended challenges for them to do. So I invite you to reflect on how you might bring one of these processes to your classroom: pattern recognition, decomposition, abstraction, algorithmic thinking, or debugging into your next activity or lesson. I have some resources here that you might like to use. I'm going to share the website at the top, that tinyurl.com/TME-innovation-lab. That's a resource we developed for the Montessori event. It's called the AMS conference. And we set up a future classroom in that space. It has the resources for all different ages. International, I don't know what happened to that N, Society for Technology and Education, iste.org/blog/computational-thinking-for-all. Of course, NAYC.org has resources, National Teacher Science Association, NSTA.org. Also, there's a great book by Bears, BERS, called Coding as Playground. That's a lot of fun. There's another an article on teaching young children, Message in a Backpack, helping preschool children with computational thinking. And then Levine, I think is her name, or his name, in 2022, creating a preschool computational thinking learning blueprint to guide the development of learning resources for young children. Joss Wick's Reading, Coding, and Crafting, Introducing Computational Thinking to Children, was in the Young Children magazine in, I think 2022. Sorry, I'll add that date before I share this. And then another great book is by McClellan. It's called Kinder Coding, Unplugged, Screen-Free Activities for Beginners. That was published in 2020. And then I'm going to try and switch screens, and because I want to just jump to that. So I'm going to stop sharing, and then I'll reshare when I get the other screen, so you can just take a look at the resources available from that tiny URL site. Can you see that now? The Padlet.
Yes.
So this has lots of resources. This is like, for example, here's a toddler lesson on what's real and what's a replica. Right? There's Venn diagram lessons. There's lessons on, these are Montessori materials, but developing 3D printer lessons for older kids, computational thinking, string art, how all that fits, story and sequencing. Uh-oh, I clicked on something. There we go. And then there's some other media options. So no matter what age you work with, there's lots of resources here that might get you started on your work. I'm going to stop sharing, and I want to thank you for attending. And please reach out to me if you have any questions.
Thank you, Pat. I did not expect to be so engaged with the material because you asked up front, what does coding mean to you? And
Yeah.
I put in the chat difficult, and Debbie said complex formulas.
Mm-hmm. Yeah.
Jessica said, it makes me think about math. And then sure enough, you went right into the math. And we were just intrigued on Moses, what an incredible way to apply mathematical reasoning in the Montessori classroom. And then we were trying to predict the pyramid triangle colors. And I was just fully intrigued with everything. So thank you. That was amazing.
Great.
Yes.
Thanks.
We thank you so much for presenting. Does anyone have any questions for Pat, Dr. Barton? And we want to thank everyone for attending as well. Joe, will you put the survey link in the chat? And please click on that link to leave your feedback on this presentation.